In this video, let's explore C++ maps, also known as key-value associative containers in the standard template library. We'll dive into what maps are, their key features, and how they can be incredibly useful in your C++ programs. First, what are maps? Maps are associative containers that store elements in key-value pairs. Imagine a dictionary where each word, the key, has a definition, the value. Each key in a map is unique and can only appear once, ensuring that there's no ambiguity when retrieving values. Elements in a map are automatically sorted by their keys, using a comparison function. This means that when you iterate through a map, you'll always get the elements in a sorted order based on the keys. Key features of maps. Maps are implemented as balanced binary search trees, typically red-black trees. This ensures that operations like insertions, deletions, and lookups have a logarithmic complexity, O log n, making them efficient even for large data sets. Maps are part of the C++ Standard Template Library, or STL, which means they are readily available and optimized for performance in any C++ environment. This makes them a reliable and efficient choice for managing data in your applications. Now let's look at some basic map operations. First, include the map header like so, #include map. Also, include the iostream and string headers. Next, in the main function, create a map with string keys and integer values using the following syntax: std, map std, string, int, ages. To insert elements, use square bracket notation, ages, Alice equals 30, ages, Bob equals 25, or the insert function, ages.insert, Charlie, 35. Let's look at how to create and populate maps. You must first include the map header, denoted as less than map greater than. Next, you define the key and value types in the template parameters, as shown in the previous code example. To insert elements, you can use the square bracket notation, the insert method, or the emplace method. Let's see how to access elements inside a map. Continuing from the previous example, we will access the map by using operator square brackets. Int AliceAge equals ages Alice. This will store the corresponding value, 30, inside AliceAge. Next, to access the elements using the at method, use the following: int BobAge equals ages.bob. This stores 25 inside BobAge. Finally, let's access the elements using the find method. Autoit equals ages.find Charlie. If it not equals ages.end, then you can print the value to the console using it-second. You can use three element access methods: operator square brackets, at, and find. With operator square brackets, an element will be created if the key does not exist. This has no bounds checking. Using at will throw an exception std, out_of_range, if the key doesn't exist. This is safer but slower. The find method returns an iterator to the element, or the end of the map. No exceptions are thrown, and it is good for checking existence of a key in a map. Here are the ways to iterate through maps. The first way is the traditional iterator loop. Start with autoit equals ages.begin. The condition is it equals ages.end. The increment is ++ it. Inside the loop, print it-first and it-second to the standard output stream or the console. The next way is using a range base for loop. Const auto and pair. Ages will iterate through the map. To print to standard output, use pair.first and pair.second. Lastly, structured binding starting with C++17 is a way to iterate through the map. Const auto and name age ages. Print name and age to standard output. Let's discuss the map iteration methods. We can use traditional iterators which use begin and end, and access via it-first and it-second. A range base for loop offers cleaner syntax, starting in C++11. Each element is a standard pair. Structured bindings, available in C++17, provides the most readable syntax and directly names the key and value variables. Maps are always iterated in sorted key order. Here are some ways to modify maps. Updating values is done by using ages. Alice equals 31. This will update the existing value, Alice, to 31. Inserting new elements can be done as follows. Ages.insert, David, 42, or ages.emplace, Eve, 28. Removing elements is done by ages.erase Bob, where Bob is the key. Or you can remove by iterator, like so, auto it equals ages.find Charlie. Check if it is valid, and then call ages.erase it. To clear all elements inside a map, call ages.clear. Here are the map modification operations. To update values, use operator square brackets or @. To insert elements, use the insert function, emplace function, or operator square brackets. The insert function returns a pair with an iterator and a success boolean. The emplace constructs the element in place. The operator square brackets creates a key if one does not exist. To remove elements, use erase, which returns the count of elements removed, or erase by iterator, which removes at the iterator position. Lastly, to clear a map, call the clear method, which removes all elements. Here are ways to check and query maps. To check if a key exists, call ages.findAlice to see if it does not equal ages.end. You can also check key existence by calling ages.countBob, 0. To check if the map is empty, call ages.empty. This returns true or false. To get the map size, call ages.size. To check map capacity, call ages.maxSize. Map query operations include checking key existence and size operations. Checking key existence can be done by calling find, count, or contains. The find function returns an iterator or end. The count function returns 1 or 0, and the contains function in C++20 returns a boolean. All these operations have O log-in complexity. Size operations include empty, size, and max size. All operations are O1. Let's see how to use custom key types in maps. First, define a struct called point. It has two integer values x and y. You need to define the less than operator for comparison. Inside the function, if x equals other.x, then return y other.y. Otherwise, return x other.x. Then create a map with a custom key type like so: std, mapped point std, string point labels. Then, insert elements with the point and the label like so: point labels 10, 20 equals point A, and point labels 5, 15 equals point B. To use custom types as keys, there are some requirements. The custom types must be comparable with strict weak ordering. You need to define the less than operator or a custom comparator. The options include overloading the less than operator in the class or struct, provide a custom comparator function, or use standard less specialization. Ensure consistent comparison logic, and make comparison operators const. Keys must maintain their ordering criteria while in the map. Here is how to use custom comparators in maps. The following example uses case-insensitive string comparison. Create a struct called case-insensitive compare. The function operator takes const standard string A and const standard string B as input. Return standard lexicographical compare. The inputs are a.begin, a.end, b.begin, b.end. Pass a lambda with character C1 and character C2 as input. Return standard to lower C1, less than standard to lower C2. The map with the custom comparator will look like this: std, map std, string, int, case-insensitive compare, name map. Let's discuss using custom comparators. You can specify a custom sorting order as the third template parameter. It can be a function object, also known as a functor or a lambda. Some common use cases are case-insensitive string comparison, custom sorting criteria, or reverse ordering. The requirements are that you must implement strict weak ordering. It should be consistent and transitive. Another example of using a custom comparator is standard greater T for reverse order. C++ has a few map variants. A standard map is ordered. An unordered map is a hash table. A multimap allows duplicate keys. An unordered multimap is a hash table that allows duplicate keys. To insert duplicate keys in a multimap, call multimap.insert, Alice, 30, then call it again with a different value multimap.insert, Alice, 31. Both entries will exist. Here are the map types in the standard template library. First, the standard map is implemented as a balanced binary search tree and does not allow duplicate keys. Standard unordered map is implemented as a hash table and does not allow duplicate keys. A multimap is implemented as a balanced binary search tree and it allows duplicate keys. An unordered multimap is implemented as a hash table and allows duplicate keys. Use the standard map when ordered iteration is needed. Use standard unordered map for faster lookups, average of 01. Use a multimap when multiple values per key are needed. Here are some map best practices and performance tips. To efficiently insert with a hint, do the following. Auto it equals mymap.begin, it equals mymap.insert, it, key 1 100, it equals mymap.insert it, key 2 200. To avoid unnecessary lookups, auto-iterated inserted equals mymap.insert, key 3 300. If not inserted, iterated second equals 300, update without a second lookup. Use in-place instead of insert when possible. Mymap.inplace, key 4 400, constructs in place. Here's what to do and what not to do. Do use reserve for unordered map, check insert return values, use in-place for in-place construction, use insertion hints when possible, and consider unordered map for performance. Don't use operator square brackets when checking existence, modify key values while in the map, forget to check iterator validity, or use complex objects as keys without proper hash and compare functions. Standard map has O login operations, standard unordered map has O1 average, and ON worst case. Consider memory usage versus speed trade-offs. Profile before optimizing. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.